and the other organizers for inviting me. As she said, my name is Benjamin. I've been a core developer of CPython for for about more than 13 years now, and I've worked on a lot of different areas. But today I would like to talk a little bit about security issues in CPython. And the form of this talk is kind of exactly what it says in the title. I'm going to talk about four different security issues in CPython that I've experienced, and in some cases participated in the diagnosis and fixing of. And I think it's an interesting window into not only security, but different parts of the language and the interpreter, and also the social community around Python and other programming languages. One of the most interesting things about security issues, I think, is that fixing them and dealing with them often requires knowing a lot about different areas and different technical details. It's a very cross-cutting concern. So the first thing I'd like to talk about, though, is that it's even kind of an open question, like what even is a security issue in a programming language? Because if you have some sort of application, like a website, it's a little more clear what your threat model is like, you're not supposed to let different users access the private data of another user. You're not supposed to get pwned and have that information stolen. And there's all sorts of well-known threats with web browsers, for example, with like cross-site scripting attacks and all those things which security people have to think about. But a programming language is not an application which end users use. It's a tool for programmers to build other things. So it's not exactly clear what threats we need to be protecting against in a programming language. And there's definitely hard limitations on how well we can do, because we're providing a tool with a lot of power. That's why I use a programming language. And we can never really prevent the user from writing insecure code. That would be impossible. So it's a interesting question to me, like what actually makes something a security vulnerability in a language. But in some cases, it's pretty easy to see that something is a problem in the language. For example, if the Python interpreter just crashes, it's without the user doing something really bad, it's definitely a problem. So I'd like to talk about a particular crash in CPython. So that's, the name CPython suggests, it's written in C, and C has pretty well-known issues with memory safety, and it's very easy to write bugs that can cause security vulnerabilities, and CPython is, of course, not immune. So an example of that kind of bug was in a module called the stirrup module. And my guess is that almost none of you have ever heard of what the stirrup module is. And so that's part of why I bring this up, because it's kind of intersects with some very interesting Python history. So way back in the beginning when Python was created, built-in types did not have methods. So you couldn't, for example, call count on string or replace or any of the other string methods. But of course, people still wanted to do with those kinds of things. So instead, there were methods in the string module which you could use to do various kinds of basic string operations. So, for example, counting. So today we would always just write count as the first argument string dot count. But in the early days of Python, you would have to use the string module. The string module is just a Python module, and it used for loops written in Python and so forth to accomplish its tasks. But unfortunately, since Python can be a little bit slow for those kinds of things, people were unhappy that the string module was so slow. And so there became the stir-op module, which was the string module, but all the functions were written in C. So it was faster to use. So this was still all very early in Python's history, and pretty soon built-in types gained the ability to have methods. And so everyone just started writing using methods on strings rather than using the string module or the stir-out module. But the functions in the string module existed all the way up for the entire existence of the Python 2.7, and it was only in Python 3 that the methods in the string module were removed, and the stir-up module was also removed. So the stir-up module was still kind of sitting around. Probably no one was using it, but it turned out since it was written in C, it had some bugs. Like if you passed strings that were too long, then it could cause the math inside of the stir-up module would overflow, and it could cause it to write into memory that it had not allocated, which is a pretty serious security bug. So it's very unlikely that anyone is using the stir-up module, but this is still a potential bug had to be fixed. Luckily, though, it's the sort of problem that was pretty easy to fix. You just had to fix the logic within the stir-up module to detect when something might overflow and then throw an error rather than try to write over memory that it did not own. So to some degree, a very old bug, but one that was probably not all that serious practically in the wild because no one knows what the stir-up module is, and two, very easy to fix. So just a few line change. Those kinds of things are not going to hold for the other issues that we're going to talk about. This is definitely the easy case. So let's talk about another issue which has to do with kind of related to performance, and that has to do with dictionaries. So dictionaries, as I'm sure you're aware, are very commonly used in Python. Not only do many people functions and so forth end up using them, but they are kind of the basis of the Python object model, so you can't really avoid using them even if you tried in any kind of non-trivial CPython code. And dictionaries are internally use a hash table, which is a wonderful data structure that I'm sure we all learned about in our algorithms class, that can use sort of arbitrary objects as keys, such as strings or integers or even custom objects, and then provide constant time access to them within the container. So, for example, in this code where we just fill a dictionary with the integers from 1 to n, we expect that to run in about linear time, which is linear to n, because the hash table provides those kinds of performance characteristics. But unfortunately, it turns out a while ago that if you pick some particularly evil inputs and put them into your dictionary keys, then you can cause the performance of the dictionary to go from linear to quadratic, which is kind of performance death. And so what actually was going on here? And so this is a concern because oftentimes people take input from users, untrusted input, and stick it into dictionaries. And so if you could change the performance characteristics of the dictionary so severely, you could potentially perpetrate DDoS attacks or other kinds of problems that would break a web app by using up all of its resources using this attack. So what's actually going on here? Well, hash tables rely on the hash codes of the keys being uniformly distributed, or at least close to that. And for anything that you'll encounter in the real world, the hash functions generally perform very well in terms of distributing hash codes uniformly across the integer space. But it turns out that you can if you feed the right kinds of carefully crafted evil inputs into the hash function, they'll end up putting all the inputs into the same bucket, which causes the assumptions that make the dictionary hash table implementation fast no longer true, and kill the performance of the dictionary. They basically turn it into kind of a linked list. The fix for this problem was to make it so that attackers could not guess the hash code of items and thus not perpetrate the dictionary, not be able to figure out how to craft bad inputs. So the first way this problem was fixed was just mixing in a random seed to every hash code for basic types such as strings and bytes, and so that the secret was generated once per process, and the assumption was that it would be difficult to guess that secret and be able to craft bad inputs, bad hash values. So that seemed to work for a little while, but unfortunately, people discovered that you could, given enough inputs, you could figure out what the secret was and defeat the whole process. And so the more final fix was to switch from the previous hash algorithms that Python was using to one called CPython, which is much more difficult to reverse engineer. And another major constraint was that since dictionaries are used so commonly in Python, hashing is used so commonly in Python, the hash algorithm has to be really fast. So another key constraint that guided the selection of CPython was that it's still a very performant hashing algorithm while being more secure. The other funny thing that this fix caused was that it made dictionary ordering less deterministic. So dictionaries are now ordered by insertion in modern Python, but that only happened in the last few years. At the time this bug happened, dictionary iteration order was not at all guaranteed. But before the randomization, dictionaries would have about the same order if you were running on the same platform, just because all the hashing and so forth was deterministic. And people came to rely on that, of course. And so this fix for any randomization actually had to be put behind a flag because it broke a whole bunch of programs because they were relying on the deterministic dictionary ordering. So it also caused users to have to make their code a lot more robust to the assumption, which they shouldn't have been making in the first place, but they were, that dictionaries had a deterministic iteration order. All right. The third issue I'd like to talk about is SSL certificate verification. So when you make a TLS connection with your browser, for example, the client has to verify that the certificate that the server sends is actually one signed by an authority that they trust, and that it's also valid for the domain that they're connecting. So Python's implementation of TLS and the SSL module supported verifying certificates. It just did not do it by default. So if you were very careful with the code you were writing to verify certificates, then you would be fine. But if you just sort of use the default settings, then you would be essentially accomplishing nothing by using TLS or SSL. And this problem propagated into the higher level networking libraries in CPython. So for example, the URL, if you just try to open an HTTPS URL that's going to make a TLS connection underneath the hood. And in older versions of Python, that would essentially be a very false sense of security, because the client would not be verifying the certificate. So you would have an encrypted connection, but you would really have no idea who it would be an encrypted connection to. The fix for this, of course, was to make certificate verification enabled by default. But that was even more painful and backwards incompatible than the dictionary hash ordering problem. And part of the reason was that, so this happened at a point when CPython was both producing new bug fix releases of Python 2.7 and releasing new versions of Python 3. And so this was considered to be such a serious problem that the new behavior was backported to a bug fix release of Python 2.7. But of course, many people had come to rely on certificate verification not happening. And so a whole other mechanism had to be added so that system administrators could turn off certificate verification again, to keep people's legacy apps working that they couldn't be fixed. So there was an entire Python enhancement proposal about how this code would be backported to 2.7 and how it would ease administrators into the fact that certificate verification was now enabled. There was also a lot of problems related to system certificate stores. So to be able to know whether you trust a certificate, you need a list of the certificate authorities that you trust, which is the role of the system store, certificate store. And how that works on every operating system is very different. So Windows has one, Mac OS has one, Linux distributions usually provide some sort of list. And you need a custom way to extract those certificates in each operating system, so that you can verify what you can know what certificates the system wants to be trusting, and that causes a lot of edge cases and things that are different on different systems, and whether people have installed different things on their system. So that was another painful part of this migration process. All right. So the final one I'd like to talk about is an issue that has been around for a long time, but got a lot of press recently because there was another paper about it. So there, the reason is that the background is that in Python 3, you can use many kinds of non-ASCII Unicode characters in identifiers. So you can write functions in English, or using a Cyrillic script, or Chinese, or cuneiform, many types of identifiers. So that's great for the wider programming world, which don't always want to write all of their identifiers with ASCII, which was designed to represent characters in the United States in like 1960. But Unicode is kind of a wild world where there are many characters which can be confused with themselves, and many complicated rendering algorithms which can cause humans to interpret a piece of text different from how a machine or a parser might interpret that. So the most basic kinds of confusion this can cause are homoglyphs. So a classic one, even in English, is the numeral 0 often looks like the capital letter O, but there are many between languages and different scripts. For example, the letter H and the Cyrillic N. So maybe if any of you have participated in, I think it's called Volapük encoding, that's the kind of tricks you play. But there, sort of the most recent paper that I was talking in press was about using bidirectional text to confuse parsers. And so that's because some languages are written right to left and some are written left to right, and some are even written top to bottom. Unicode provides a way to render right to left text within left to right text. And that can be confusing to parsers and humans. So for example, this is, and one of the examples from the paper is, it's possible that you and I could see these two lines, which look exactly the same to us, but the second line may actually cause y to be assigned to the variable rather than x. And that's through some really terrible subterfuge where you insert bidirectional text markers into the comment, which causes the code to be displayed like this, but the actual code points, if we looked at the binary text file, would be in a different order. So this means that the code that I'm looking at, the code that I'm reviewing, the code that I think that's running might be different than what the computer is actually seeing. It seems like this bug was reported to almost every modern programming language. So I definitely know at least Go and Rust and Python got this, and everyone reacted in a little slightly different way. So some people said, well, this is not even actually a programming language bug. This is a bug in text editors or code review tools. They should be showing that something weird is going on here. It's not our fault. Rust took the approach of just banning bidirectional marker characters in Rust source code. Python took the hands-off approach, but we did get this Python enhancement proposal, Unicode-related security considerations for Python, which talks about the kinds of confusion attacks that I was talking about, like the homoglyphs, and discusses how they can mitigate it and why CPython didn't take any action to try to ban these at the language level. But it's not. It's a problem that shows up in many domains. I know this also happened with URLs when internationalized URLs were introduced. There was a lot of people worried about homoglyph URLs. So it's definitely still a open issue, but there's more awareness of it now. All right, the last kind of thing I would like to touch on is how security processes intersect with open source, particularly open source, which is run by people who are volunteering their time. So I've found that dealing with security issues for open source projects is one of the least fun parts of contributing to open source, because having a security issue means that you or someone else in the project messed up, and basically no one is going to be happy with you. Your users are not going to be happy because there's a security bug and they have to update, and maybe the security bug causes backwards incompatibilities. And if you're not fast enough, the security researchers won't be happy with you, and then they'll publish a post about how you didn't respond to their security issue if you're not fast enough. And generally, it's just not a very fun thing to deal with as a volunteer. So I would just encourage everyone to be empathetic and sympathetic to open source projects which are dealing with security problems, because it's a lot of work. All right, so I've talked about a few different examples of security issues in CPython. What are a few conclusions that we can try to draw from this? So I would say one thing is that there's a whole lot of types of security things that we consider security vulnerabilities in a programming language. And many of them go quite deep into how the language is implemented and data structures and various semantics. Most of these issues I've talked about, I could give almost an entire talk diving into the problem and how they're fixed, but I was just only able to give a summary in the time allotted. But the other thing is that it's not a static environment. So, for example, the SSL certificate the fact that the SSL module did not verify certificates was an issue since the SSL module was added, which I think was in Python 2.4. But HTTPS became much more prevalent after that, especially since browsers pushed to have most websites use HTTPS, and it became the expectation that we would always be communicating over networks with in a secure manner, and so that kind of made it much more important that certificate verification be on by default. And the other thing is that it being possible to be secure, but it not being the default can also be a security bug. So again, with the SSL verification, right? It's not that you couldn't do it; it's that it was not the default, and therefore most programs would be insecure because people are busy and don't have time to check every single line is doing the correct thing. And perhaps the final thing is that Hiram's law, which says that any kind of behavior in a sufficiently used API will be depended on, definitely applies to security bugs and changes related to security bugs. So, for example, fixing the dictionary performance problem changed the order of dictionary iteration, which was never guaranteed by Python, but people depended on it anyway, and when it broke their code. And similarly with the security SSL verification problem. So it's kind of this security brings in a whole bunch of different parts of software engineering that we end up having to consider. And with that, I will conclude. Thank you very much for your attention, and thank you again to the organizers for inviting me.
Yeah, thank you, guys. Do you have questions? Any? Please write us. We have time just for one, maximum 2 questions. And Benjamin, thank you a lot that you joined and told so much about various security issues. By the way, I will drop the link to your Twitter where people can find links to your blog where you write about empathy and being sensible while reporting different bugs.
I definitely complained about the security source things before.
Yeah. So I dropped the link. People can find it and read. Actually, very interesting article. Well, the last that I read. If there is no question, if you can very briefly answer, what's the future of CPython? In 2 words, let's say. You're on mute. Benjamin,
I had to think anyway. More bugs. That's a good guess with any piece of software. I mean, Python has grown so much over the time that I've been working on it. It's just amazing, like how universal it is now. And now there's a lot of focus on performance and also advanced features, and there's just so much more activity. It seems now. So that's not the greatest answer, but that's.
Mm-hmm. You see another question on your screen. Is there any simple text to roll into Python contributions? Is there any need in C developers?
Yeah. So I mean, there's let's see. So there's lots of open issues, and some of them involve C. CPython is often not the easiest project to get started in, I would say, because it's often true. It's for such an old and mature project. Uh, Most of the easy issues have been fixed, and so many of the things that are open are like not so much code changes, but like thinking about the best way to design something, or the best way to make a change that causes the least amount of breakage, and lots of like questions that require a lot of thinking. So there's always things to do. You can look at the issue tracker, but I would just caution that it's not an easy on ramp.
Thanks. One more thing is about Rust. Two people asking about that. Rust Python interpreter as a way to fix some issues related to C and safety.
Yeah, I think. Well, in general, I think Rust is great. I'm glad that we're no longer have to write things in C and C++, and suffer the consequential undefined behavior bugs. I think it's very exciting that people can write C extensions. Well, not C extensions, write extensions in Rust, so Py03. I haven't looked a lot at the actual Rust Python implementation itself, but yeah, in general, the less C, the better. So.
Sorry, guys, we cannot answer all of your questions.
I will say Python 2 is done. We're done. It's gone. No Python 2.
If you will have time, maybe you could join the stream link on YouTube and answer people, because we need to start the next talk.
Yeah, sure.
Just one tiny thing we ask everyone: Poetry or PyPy?
I don't use either.
Oh, okay.